Oh, I think.
Alrighty, everybody ready? Everybody ready? So, first thing I wanted to show you today is the Mac thing, right? So I've been playing a little bit with XNA on the Mac, using MonoDevelop and using MonoGame. And I got it all working yesterday with Android, but the Android emulator is very slow, whereas the iPhone emulator is actually great. So it took me about an hour to figure out how to get the whole thing set up this morning. But once you have the whole thing set up, it is actually trivially easy to take any of your XNA projects and get them working on an iPhone or an iPad. And I'll show you. I won't do it, right? But this is the little, just to show you, to make zero code changes. It's just a matter of setting it up, right? And another day, if you're interested, I'll show you how I set this thing up. But basically, there's my game1.cs file in MonoDevelop there, okay? And this is a very, very simple little class that just loads a 3D model and draws the model. You know, it's the Dardic one. It just draws the Dardic model and runs it. But that's literally zero code changes required to do that. You have to add one extra class, which is this thing here. Yep, this is it. This is the only thing you have to add, but you can download this. Let's see, it's a Command Alt and Plus to zoom in. There you go. That's the only thing you have to add. Anyway, that's it. The MonoGame project, and let's just start debugging the thing. And watch what happens. Any of my C# programs that I've put up on GitHub, you can do this too. You can take them and you can get them running on an iPhone like this. It's $79 for the full version of MonoDevelop. That's the student license for it. So I've been on to the MonoDevelop creators, and I'm going to buy some licenses for it. Basically, anyone that wants to do this, college will buy you a license, okay? Or you can use my one. Basically, that's not going to be a barrier to somebody getting any of their project work or any of their assignment work up on the App Store. All right, I want everybody, even your third year assignments, anything that you've done in XNA, basically. You can get it running on the iPhone. You can do all your development, get it all running in touch, even get it running on Windows Phone 7. And then it's trivially easy to get it ported to the iPhone or to iPad. Some of your big full-screen games probably work better on the iPad, I would think, wouldn't they? Whereas anyone that's done a phone game, it's very easy to get it working on an iPhone. That took me about an hour. Most of that was setting up the thing. In fact, all of that was just setting it up and figuring it out.
Would you recommend doing the coding in Windows in Visual Studio and then?
Makes no difference. You can do all your coding. The only thing that you absolutely need to do, I think you can still get your content in just by dropping the files into the content folder, and then you're just loading them up as files. But the documentation and the YouTube videos that I've watched suggest that it's more efficient if you take I think they're called XNB files that Visual Studio creates. So there's my Dardic.xnb. So that comes from a Visual Studio project. So if you have Visual Studio running somewhere, you can basically build these files from any content that you need, and then you just drop them into this project, and then you have them available. So equally the same thing for for images and audio, whatever. You just drop them in. It makes these XMB files out of them, and you just drop them into your project then, because there's no content pipeline. The command line tools to make the content into these XMB files are not available outside of the Visual Studio. But anyway. What do you think? It's good, isn't it?
So you're not using Xcode at all?
No. The whole thing is MonoDevelop. You use Xcode if you want to do something like a standard iPhone app. In other words, you need to use Interface Builder, and then you need to use Xcode to do the interface. But actually, all the coding is done in MonoDevelop. And MonoDevelop is a clone of Visual Studio. Even the keystrokes, for the most part, are the same. The keyboard shortcuts and things. So anyway, that took me no time to get working. So I'd be really excited to see what you guys can come up with. And obviously, the iPhone, the iPad are huge platforms, and there's potential to get a really, you could easily get a few thousand downloads or even more with your apps. What do you think? Who's going to do it? Who's not going to do it? If you're not going to do it, I presume it's because you're doing Focus 2D X. That's fine. We'll talk about the assignment in the second hour of this, but I do want to speak about how we award the marks, because some people are doing Dublin Gamecraft this month, and some people are porting their games to Mono and getting them on the App Store, and I want to make sure people get marks for all of that extra stuff that you do. In other words, your portfolio of marks. So I'm going to give maybe 20 or 30% of your marks in the assignment for all of that stuff, your portfolio. work, you know, whatever you've done over the semester. Okay? And equally, if somebody decides to do a competition with your assignment, then you got to get marks for that. That's fair. All right? So the things I'm really looking out for are people that are doing, number one, a competition, number two, getting something on an app store or a marketplace or other. You will get your 20 marks, bonus marks for doing that. Is that all right with everybody? Or using the Havoc SDK because it's complicated. So you get marks for doing anything that's particularly complicated or doing something which is commercially orientated. Alrighty. So, okay, the first part of this class, I'm going to go through all this Quaternion stuff, and we're going to nail a lot of the Quaternion stuff today. The plan is, right, I'm accelerating this a little bit because I want to start doing the BPU physics stuff with you next week so that you can start working on your assignments. But what we'll do is we'll probably do all the BPU stuff and then come back and look at this in a little bit more detail later on in the course. And there's some other things like cameras that we barely touched on that we'll have to come back and work on a little bit later in the course. But I'll do the BPU stuff first so that you can start working on your assignment. Is that alright? So the Quaternion things. Quaternion in XNA is just Quaternion. So you just go Quaternion Q. And then you can go Q.W, Q.X, Q.Y, and Q.Z. So the first thing is, how do we make, what is a Quaternion? Can anybody tell me first of all? What's it used to represent? It's used to represent the rotation or the orientation of an object in 3D. Okay, how do you make a Quaternion? What's required to make a Quaternion? Two things. An axis of rotation and an angle. Alright, so to make Q, you go create from axis angle. Typically, how do you create the axis? Typically, how would you create the axis of rotation? In a typical scenario where you need to make a Quaternion to represent an orientation of something. You use the cross product of two vectors is typically how you're going to make the axis of rotation. What does the cross product give you? If you cross two vectors together, you get? Do you get a vector or a scalar?
Vector.
You get a vector. What's the significance of the vector?
Perpendicular.
It's mutually perpendicular to the two vectors. What's the significance of the order in which you do the cross product? Does it matter? If you do A crossed with B, is that the same as B crossed with A?
No.
So what's the significance of the order in which you cross them? What's the difference between A crossed with B and B crossed with A?
The direction of the axis.
Exactly. It'll give you the direction of the vector that you get back, right? So if you were to take these two vectors, that one and that one, and you get the cross product of those two vectors, depending on which order you cross them, you might get a vector which points out of the whiteboard, or you might get a vector which points into the whiteboard. The order in which you do the cross product is called what? Anybody remember? It's got a special name in graphics programming. Called the... You have the same thing when you're programming what's called a vertex buffer. In other words, if you have a block of memory on the graphics card, the order in which the vertices make up the triangles, it's called the winding order. So this is called the winding order. And you guys should take notes, right? So it's the winding order of the vertices, tells you the winding order. So the angle of rotation is typically given by, how would you calculate the angle of rotation for a Quaternion? Typically it's going to be the something of two vectors. The dot product. Okay, so you're going to use the dot product to calculate the angle of rotation and the cross product to give you the axis of rotation. So it's using that equation, A dotted with B over the length of A times the length of B, and then you get the inverse cosine of it, and that gives you the angle between the two vectors. So that's how we create a Quaternion. How do we rotate a vector by a Quaternion? How do we rotate anything by a Quaternion? What's the equation for that? So it's a really simple equation. The multiplication of quaternions is complicated, but this equation is pretty straightforward and very fundamental, and you need to know it because there's most definitely exam questions on this. And it's fundamental to your understanding of why we use quaternions as well and how useful they are. How do you rotate a vector by a quaternion? Anybody remember? Do you remember this one? Q equals W times Q times the inverse of. Or is it the other way around? Do we say W equals Q times W, yeah, multiplied by Q inverse. So that's the equation. That's the equation, and sorry, that should be really multiplied by, to distinguish between the dot product. These are the cross product of two quaternions. I don't know if there's a dot product of two quaternions defined, to be honest. I don't know if it's defined. The thing is, when we're talking about multiplying, in this particular context, we're talking about the cross product of two quaternions. The cross product of two quaternions takes about half a page, or at least one big full screen, to write out how you calculate it. It's just a whole load of addition and subtraction and multiplication of the elements of the two quaternions. But you don't never need to know it. You use the multiplication operator overloaded, of the quaternions in order to do it. So this is how you rotate a vector by a quaternion, where Q is the quaternion you want to rotate. W is what? Can anybody remember? This W on this one here. It's the pure quaternion made from the. It's a pure quaternion made from the vector. Yeah. That's the pure quaternion made from the vector. So how do we make the pure quaternion from the vector? Can anybody remember? The x, y, and z of the vector comes from the x, y, and z of the quaternion comes from the vector. So q dot x equals the vector x, q dot y equals the vector y, q dot z equals the vector z, and then q dot w is equals to 0. So you set the w component equals to 0. You multiply them out like that. How do you get q inverse for a normalized quaternion? How do we get q minus 1? Q inverse. Sorry? You negate the x, y, and z, alright? So q, that one, is equals to just negate the x, y, and z. And then you just take the w as whatever it previously was. So if you multiply those out, that will have the effect of having rotated the vector by the quaternion. So, yeah. We have a special quaternion, which I don't know if I mentioned. Did we talk about the identity matrix? What's the identity matrix? Can you tell me? Exactly. So the identity matrix is this, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. What's the significance of the identity matrix? What would you get if you multiplied another matrix by the identity matrix? You get the same thing. So it's like saying something multiplied by 1. It's the same as you get itself back, right? That's called the identity matrix. It's just the one with the diagonals. And you can try this out yourself. You can multiply a row matrix by that, and you'll end up with the same row matrix at the other side. There is an equivalent in the quaternion. And the equivalent in the quaternion is the quaternion that if you multiply, or you try to rotate this by the identity quaternion, it would involve no rotation, because anything multiplied by the identity quaternion is itself. Alright? So if you want to specify, for example, something equivalent to the basis vector for a quaternion, you have an orientation, you're saying that the model, when you load it up, the model points down the negative z-axis, so what rotation has been applied at that point? There's a 0-degree rotation. You can say it's the identity quaternion. Do you understand? So it means no rotation, essentially. And the identity quaternion is that w is equals to 1, the x, the y, and the z are all equals to 0. And that's called the identity quaternion. Alright. So, yeah. Let's see. Can anyone lend me a page, just so I can read a word with? Thank you. Next thing about the quaternion. At some point we need to take our quaternion and we need to make it part of a world transformation matrix. So how do we do that? Remember the poem. To convert a quaternion to a matrix, we use the API. So there is a little algorithm which you can look up if you really want to. But basically you just go matrix dot create from Quaternion, I think is actually the API call. Matrix dot create from Quaternion. Alright. How would we combine multiple quaternions, and what does it mean when we combine multiple quaternions? First of all, what does it mean to combine multiple quaternions? Yeah, it means that you do one rotation followed by another rotation, or it combines the two rotations. But in the same way as matrix multiplication, quaternion multiplication is not, what's the word, associative, commutative. So it means that, you know, if Q is a quaternion, Q1 multiplied by Q2 multiplied by Q3, that's not the same as Q3 multiplied by Q2 multiplied by Q1. So these two are not the same. And there's the answer to that other question. How do you combine quaternions? You combine quaternions in the same way that you combine matrices, by multiplying them together. And this is the effect of doing this rotation followed by this rotation followed by this rotation. Yeah? So you can, you know, we might write a C program, just a console program, just to take a vector and apply a number of rotations to it. And you'll see that it's, you know, if you multiply the three quaternions together, you basically get, you know, you can go something like Q equals all of these rotations together, and you get one quaternion which represents the three rotations combined together. Do you understand? So it's like doing one after another. But again, just being clear that the order in which you do the rotations is obviously critical. Okay, so what else have we got in terms of the fundamentals of quaternions? The next thing about quaternions is we have this algorithm, which I'm going to write out. It's not that difficult, right? It's the quaternion slurp algorithm is given as this. Slurp T, A, and B. Where A and B are quaternions and T is the, I don't even know how this works. 1 minus T times theta over sine phi. Okay, actually it's not that hard. It's sine of 1 minus T times theta all over sine of theta times the first quaternion plus the sine of theta, T times theta, P over the sine of theta. Much cleverer people than me have worked this out. I don't know why that is the case. I'm sure a mathematician will be able to give you the derivation for that, why that works. But that's the slurp function for a quaternion. So knowing this bit is not important, but knowing the API parameters is kind of important. Okay, so A and B are two quaternions. What's T? Is T a quaternion, scalar, vector? Remember we did it in the lab on Tuesday? T value for it, it's a scalar. Alright, so this is a float. And this typically goes between 0 and 1. If you pass in 0 for T, the function gives you back. What does it give you back? Gives you back. Gives you back the first quaternion. Gives you back A. Right? If you pass in 1 for T, it gives you back B. If you pass in 0.5 for T, what do you get? You get a rotation which is exactly 50% of the way between A and B. So this, from a rotational perspective, I think I'm going to probably do a nice little program which draws a globe and does this on a globe, because it'd be pretty easy to do that. Actually, you know, you can even do it from a circle. You know, like imagine this is basically a slice through a sphere, and you have a quaternion which is representing this rotation here, and you have another quaternion which is representing this, or this orientation here. If you pass in 0.5, you'll get something which is basically halfway in between them like that. And then passing between, you know, 0 to 1 gives you values between those two quaternions. What would happen if you passed in a number which is greater than 1? The universe would end, and all life as we know it. Believe me? Huh?
Better not do that.
Well, okay. We could try it just to see. I tell you, it's not as bad. It's not as bad as that. It's actually not bad at all.
Would it just return B?
No, good guess no. What you actually get is you just get something which is in the same direction as A to B, but beyond B. And the same way if you're passing something which is less than 0, you get something which is less than the first quaternion, but in the same direction, around like that. The algorithm, I think, is really easy to understand, the vector version of this algorithm, which is just called the lerp algorithm. And the lerp algorithm, lerp, T, A, and B, stands for linear interpolation between A and B. And that's really easy. That's just A plus B minus A times T. That's the linear interpolation algorithm. It's really simple when you think about it. You know, you're given, say, if A was 5, 5, and B was a point 10, 10, then the vector B minus A, that's B, and B minus A is going to be the vector 5, 5, isn't it? Because it's B minus A. And then if you pass in 0, then you have B minus A times T, which is 0, so you get back A. And then if you pass in 1, then you have B minus A multiplied by T, which is going to be the vector 5, 5, because it's multiplied by 1, plus the vector A. So 5, 5 plus 5, 5 is 10, 10, so you get back B. And if you were to pass in 0.5, you'd get something which is halfway between those two. Do you understand? So next time you're playing any computer game and you see a character doing this, turning its head, raising its arm, now you know how it's done. It's all done using Quaternion interpolation. You know, this is one orientation, turning over to face this new thing, this is a new orientation. And that slow movement from one orientation to another is pretty much always done using Quaternion interpolation. Cool or what? Alright, that's the kind of fundamentals of quaternions. That's quaternions to represent angles. Can't really think of anything else to talk about on that one. But now we move on to the sort of the integration bit, which is basically how you integrate quaternions. And what we'll do is we'll explain the equations first, and in the second part of the class we'll write the code to do it. And you'll see that this theory anyway is at the heart of all the physics engines, even though they use a different way of doing the integration. So, first of all, we've been programming the forward Euler integration, yeah, for a particle. That's our explosions and all that are implemented as a forward Euler integration. The entities in our scene keep track of a number of different pieces of state, don't they? So each entity has got what? Every entity in our game is going to start out with position, right? What else does it keep track of?
Whether it's alive.
What's that?
Whether it's alive.
Well, yeah, definitely. But we'll just think about it in terms of the actual physics of it, right? In terms of the physics, it keeps track of its position. A look vector, sure thing. What else does every entity in the scene keep track of?
Up, right,
What's that?
up.
Yeah, so we've got look, up, and right.
Velocity.
Every entity has a velocity, okay? And related to velocity is the speed. So, yeah, what else have we got? Okay, I'm going to give you a physical example to illustrate. Whoa, this arm is really, this one has, yeah, you got it. So every object has mass. So in order to implement a physical simulation of an object, we need to keep track of a few other things, don't we? What else do we need to keep track of? What's that?
Force.
Force, yeah. Force, we call the force, sorry?
Force applied.
Force applied, yeah. So in terms of the keeping track of it, we call it the force. Because what happens, you know, if you have a spaceship, and the spaceship has got a thruster at the front and a thruster at the back, and the two thrusters are going at the same time, does the spaceship move? What happens? The forces, they cancel each other out. Alright, so you add up all the forces together, and they can potentially, it's called a force accumulator, right? Force ACCUMULATOR. So we have a force accumulator. And each frame, you basically sum up all the forces acting on the object, you apply those forces using the laws of motion, and at the end you go force accumulator equals 0. So you reset the force accumulator, because otherwise it's like turning on the thrusters and leaving them on. So we've got position, look, velocity, speed, mass, force accumulator. That's everything, isn't it? Of course we have a few other things in there as well. We have its world transform. And then we need a couple of other things just in order to do the integration. What else do we need? We need at least 2 other things. To do the integration, we need to know the time delta. All right. And we use the forces to calculate what? We use the force accumulator to calculate D. The force accumulator doesn't directly cause the object to move. It doesn't. It causes the object to accelerate. So we have acceleration. So these things are things that we calculate and throw away. Okay, all the rest of them are kind of state that we keep track of, but this is stuff that we calculate each time step. Now, position, look, velocity. What's their format? What are they? Are they scalars, vectors, quaternions, matrices? They are vectors. These guys are vectors. Okay, the unit of measurement for position is what? Position, unit of measurement is meters. Alright, so position is meters. The look. What's the significance of the look? What's its length? It's always 1. Okay, so that's what we call a normal. The same with the up and the right. They're all normals. We're going to keep track of those as they're all normals. We got to renormalize the normals every now and again. The velocity. What's its unit of measurement? Meters per second. So that's in meters per second. What's the relationship between velocity and speed? Is speed a scalar or a vector? Speed is the scalar version of the vector. What's the relationship between velocity and speed? The length. Okay, so speed is the length of the velocity vector. You can calculate the velocity by taking the speed multiplied by the speed multiplied by the what will give you velocity? The direction, which we call the look vector. So the look vector is of unit length. You multiply speed by look, you get velocity. So that's the relationship between those three values. What about mass? Scalar, vector? Scalar. And its unit of measurement? Grams, kilograms, things like that. The force accumulator, scalar, vector. It's a vector as well. And the unit of measurement for the force accumulator? Newtons. The world transform, we all know what this is. It's a matrix. Alright, the time delta, scalar, vector, it's a scalar. Unit of measurement? Seconds. Acceleration, scalar, vector. It's a vector quantity as well, because you can be accelerating, decelerating, you can be changing your velocity in all kinds of different directions, okay? And the unit of measurement for acceleration? Meters per second per second. So it's the change in velocity every second. Alright, that's what we already have. And the equations that we use to integrate these things, 3 steps. Step number 1, calculate the acceleration due to the force. And that's going to be equals to A equals what? Force divided by mass. So force over mass, that's the first thing. Acceleration equals force over mass. Second stage, velocity plus equals to acceleration times the time delta. So velocity equals velocity plus acceleration times the time delta. So the amount of acceleration that's applied multiplied by the time delta. That's how the velocity changes. And then finally, step number 3, you have the position is equals to, or the position plus equals to velocity multiplied by t. That's the forward Euler integration function for a particle. So now we're looking to see, because we know that in the real world, things don't always look in the direction in which they're moving. And also some forces don't cause an object to move, they cause the object to watch my hands. They cause the object to rotate. Very good. So some things cause the objects to rotate but not move. So we have to add a whole load of new variables and a whole load of new equations to the forward Euler integration function. And when we do this, it becomes a Hamiltonian integration function, because Hamilton invented the Quaternion. I get my other notes for this. Okay, first equation that we have is we have this new quantity called TO. And TO stands for torque. So the sort of, I suppose, really quick definition for torque. Torque is rotational force. Alright? There is an equation for torque, right? And the equation for torque, and you can rewrite this equation depending on if you want to calculate the force, the torque, or whatever. The torque is equals to the position where the torque is applied from crossed with the force. Alright, so that's the first new equation that we have. The position on the object crossed with the force. So, there's an interesting thing. When we do the cross product, first of all, we get a vector which is perpendicular to these things. Isn't that right? So the torque is kind of perpendicular to both of these things. So let's imagine this. I don't know if I have a good example, right? But let's say we take this physical object here, okay? Right? Let's imagine I apply some force to this object at this point here. All right? So what's going to happen with the object? It's going to rotate. The axis of rotation is going to be, it's the kind of the y-axis really, isn't it? It's the straight up axis. Okay, so the first thing to say is, here's the vector, which is the position on the object. This is the origin, we'll say, right? Here's the vector, which is the position on the object. It's here. Here is the force vector coming in this direction. The torque then is this direction here. You understand? So you cross the force with the position on the object and you get a vector which is mutually perpendicular. So the torque is always specified as kind of like an axis. You follow? And then the next thing to say is, right, if I apply my torque here, it's going to rotate in this direction. If I apply my torque here, it's going to rotate in this direction. Let's imagine that instead of applying it here on the object, I apply it very close to the center of mass. What's going to happen? I apply the same amount of force, but what happens? Does it rotate as much? No. Okay, so the closer you are to the object's center of mass, the less rotation is applied. And that's what this equation actually captures. Can you see that? So in other words, if you're right at the center of mass, then the amount of torque is going to be, it'll be 0, right? Because if you're right at the center of the object and you try and turn it right at the center of the object you apply the force, you get no torque. You know, it's kind of, I don't know, it's technically not possible. You know, but it's, I don't know, you can't really apply it. But the point is here that the closer you are to the center of mass of the object, the less torque is applied, all right? And then the torque is, if you like, applied around the axis of rotation. So that's what that equation is capturing, right? So, torque is kind of like the force accumulator. Previously we had a force accumulator, now we're going to have a torque accumulator. And we'll be able to add torque directly. You know, you can apply torque to the object. You just apply the axis and then the scale, you know, and then that will apply some rotation to the object. Or you can apply force at a point on the object, in which case you have to calculate that force might have also generated some torque, but it also applies some force as well. So, so you can calculate the torque from the force. If you apply some force and you know where it is on the object you've applied it, you can calculate it. Okay, we've got a couple of other equations. The torque is the first relationship. You know, and torque basically corresponds to force in the Newtonian physics thing, right? The next thing is, we've got another one here which is called the angular velocity. So we have velocity and now we have angular velocity. So the angular velocity tells us, what would you think it tells us? angular velocity.
The angle
Okay,
of
then
rotation is
rotate,
the
speed of rotation.
Yes, it's the speed of rotation, really. Okay, so by how much this thing is rotating every second. So the angular velocity is going to be measured in,
Radius per second.
yeah, it's going to be measured in radians per second. Is it going to be a vector or a scalar or a matrix or what? It's a vector quantity, all right? So angular velocity is a vector. Torque is also a vector. We've got angular velocity, so this is another piece of state we need to keep track of. Things can be rotating, but the rotation can be increasing in speed or decreasing in speed. So because of that, we also need to keep track of another one here called angular, Angula, or angular acceleration. Unit of measurement for angular acceleration. What do you think?
Radians per second,
Radians per second, right? So it's the rate of change in angular velocity. So it's radians per second. Again, vector, scalar, what would you think? It's a vector, so it's another vector quantity. So we've got angular velocity, angular acceleration, we've got the torque. Yep, we got one more then. And then we have enough state and we can go through the equations. Okay. What about the shape of an object? Does the shape of an object have any impact on how much rotation is caused when you apply some torque to an object? Does the shape of it affect that? Definitely, it definitely does, right? You think of an object which is this shape here, right? And if you apply some torque at this point on this object, it's probably going to spin like this. If you take the same object and it has a completely different shape and you apply some torque like this, you know, it's going to spin in kind of a different way. And basically the shape of an object has an impact on, you know, how the torque affects the object. Yeah, okay, so that is described by another piece of state that we need to keep track of, and that is called the inertia. And in fact, the inertia is described as the inertial tensor. So what is the inertial tensor? The inertial tensor, what do you guys think? Scalar, vector, matrix, quaternion? Huh? What did you say?
Matrix.
Oh, how did you know that? It's a matrix, all right? The inertial tensor is a matrix. What's the dimensionality of the matrix? Oh my goodness, very good. Reading ahead. It's a 3x3 matrix. The inertial tensor is a 3x3 matrix, as opposed to, you know, the world transform, which is a 4x4 matrix. All right. So what is an inertial tensor? A tensor is just a mathematical term for a matrix. Right? I don't know why it's called the inertial tensor. It's the inertial matrix, but a tensor is just a matrix, and it's a 3x3 matrix. How do you calculate it? Does anybody know? How would you generate it? Anybody? Any ideas? Yeah, the answer is look it up on Wikipedia. Right, there are tables for inertial tensors for differently shaped objects. Right, so let's look it up on Wikipedia. I'll show you. Again, this is something you don't need to know. Your physics engine. When you create an object in the physics engine, one of the things you have to set up is the shape of the object. You tell it whether it's a square-shaped object, a round-shaped object, and that determines the inertial tensor. And then it goes and generates the inertial tensor for you. No networks. I'll turn on my Wi-Fi. What? portable Wi-Fi hotspot. I'll turn that off. Let's see something going weird in this shoddy operating system. Oh, DIT Wi-Fi is now connected. Alrighty. List of moments of inertial tensors in Wikipedia. There we go. So here's your table which describes how you create inertial tensors for differently shaped objects. So that's a solid sphere, that's a hollow sphere. You know, it's two, you know, basically the dimensions, the m is the mass, r is the radius. So it's 2 over 3 mr squared, 2 over 3 mr squared, and so on. Right circular cone, there's a slender rod, you know, which is orientated along the y-axis and various different things. There's a different one with a different sort of orientation, and you know, a solid cylinder. Basically, you know, these inertial tensor tables, and these tables are all coded into physics engines, right, for generating inertial tensors. Okay, so the inertial tensor describes how the object is going to be affected by torque. So if you were writing a physics simulation from scratch, you would just encode these tables into your physics engine, right? So the last thing then is the actual equations. And the equations, yeah, here we go. Yeah. Okay, so first of all, here's our first equation. The torque equals the position where the torque is applied crossed with the force. That's the first equation of motion. So if we look at our thing over here, first of all, we're calculating acceleration, velocity, change in position. Okay, now we have to do the same thing for rotation. We've got a torque accumulator. We need to first of all calculate the angular acceleration, and the angular acceleration is equals to the torque multiplied by 1 over the inertial tensor. Or I think that just means the inverse of the inertial tensor matrix. Alright, that's equation number 1. And I got this from a book. So, I've implemented it, and it kind of all works. Alright, and we'll code it up in the second half of this class. And you can see when you code up all of these equations, you're able to make a flight simulator. You're able to make something which you can apply torque, you can apply yaw, pitch and roll, you can get the thing to fly around if you implement these equations correctly. The next one then is the angular velocity is equals to the angular velocity plus the angular acceleration multiplied by time delta. Alright? So the angular acceleration is equal to torque multiplied by 1 over the inertial tensor. The last one, the orientation. The orientation, by the way, we forgot to write up on our list of entities or the list of things we need to keep track of the state of. The orientation is going to be what? Vector, scalar, Quaternion, matrix. The orientation of the object is a... Anybody? It's a Quaternion. Yeah, so the orientation is a Quaternion. We're eventually going to take that orientation and make it into a world transfer matrix so that the thing will rotate. And we can draw it in a rotated position. So the angular acceleration, angular velocity, orientation is equal to the old orientation plus the time delta over 2 multiplied by w multiplied by the old orientation. This comes from the book which I've recommended on the course. There's a link to it on the website. You know, it's Game and Physics Engine Programming. And all of these equations come from that book. And I've implemented them, and they all kind of work. So the next thing is the orientation is just the orientation. W is the pure Quaternion made from AV. Now, the thing I haven't put on my notes here is what you set the W component of the pure Quaternion from. So I guess it must be, how I set it? It must be either 0 or 1. But I have it implemented in code so we can check the code. I think it's probably 0. So it's the pure Quaternion made from the angular velocity. Okay, so those 3 equations, if you add them to these 3 equations, and then you add the whole lot of stuff to do with recalculating the look vectors, the normalized, you know, I mean, there's a few other things you need to do here. For example, you might decide that you want to be able to add thrust from the thrusters at the back of a spaceship. So you need to know in which direction to apply the thrust. So you need to know the object's look vector, and you need to know the object's right vector, so you can apply sideways thrust, and things like that. So from all of this, we need to calculate, these are the simple things, and then we need to recalculate the look vector. So how would we recalculate the look vector? So previously we'd recalculate the look vector by basically saying if the velocity is greater than 0, we normalize the velocity into the look vector. So we're always traveling in the direction in which we're looking. From this, how would we recalculate it? I mean, in this you need to kind of understand what's the relationship between this and the look vector, the orientation of the look vector. Again, imagine, I should have brought my spaceship. Imagine this is your spaceship. This is the front of your spaceship. I need my look vector because I always want to apply thrust in this direction, because I want my object to be able to shoot off in the direction in which it's pointing. So here's my orientation, which is telling me the direction in which the thing has been rotated by, My basis vector is 0, 0, minus 1. Okay, my basis quaternion is the identity quaternion. So now I have a new quaternion, which is telling me the new way this thing is rotated. So how do I calculate my new look vector?
Your orientation and the basis.
Yep. How would I calculate a new look vector based on the orientation? No, it's much simpler than that. Well, of course, there's a little bit of work in it. Yes, there's a cross product and the dot product and various other things. But in fact, no, there isn't. No cross products or dot products. We have the orientation. We don't need a cross product and dot product.
That's on the basis for the...
Exactly. So you just rotate the basis vector by the quaternion. If your basis vector starts out at 0, 0, minus 1, your object is now rotated by a certain quaternion. You just rotate the basis vector. How do we rotate the basis vector? How do we rotate any vector by a quaternion? Do you remember? It's Q equals W times Q. Didn't we call it W equals Q multiplied by W multiplied by Q inverse? So you can just do that with the basis vector, and that gives you your new look vector. You do the exact same thing with the right vector and the up vector if you want your object to be able to move around in full 3D. Just take all of those vectors and rotate them by the quaternion, and you get your new look vector, your new basis, your new right vector, your new up vector, look vector, etc. Alright, I'm going to reboot the Windows here. Hey, wouldn't it be an interesting adventure if I tried to get... No, because you see, I don't know how to do the keys to apply the forces. I was going to say we could get it working on the iPhone, but I don't know how to do the keys. I'd have to figure out some way to do touch. So I'll just reboot the Windows, okay? So I got 512 gigabyte solid state hard drive there, and I installed it over the weekend, and also put Windows 8 on it, and now it runs like the wind. It's really fast. Switch operating systems before you've even said the words switch operating systems. And Visual Studio starts up instantly. It's great. Practically instantly, within 10-15 seconds. There. See that? That's what computer use should be like, huh? Okay. I'll open one of my recent projects, which is the Quaternion integration. So before we go through the code, I'll just show you what it looks like. So this is a whole set of equations implemented. And then you get a spaceship. And the spaceship is just hovering there. Well, it's not hovering. It's just there's been nothing applied to it at the moment. No forces, no torque. So the first thing you can do is you can apply torque. You can apply, in my case here, I don't actually apply the torque at a point. I just literally apply the torque around the axis of rotation. So when I want this thing to yaw, I apply the torque around the y-axis, so my torque is going to be basically multiples of the up vector in this case, you know? So I think it's these keys to rotate it. Yeah. So this is me applying the torque, you know, around the up vector. And then I can also apply, oops. Now this has got bugs in it, so it doesn't always work perfectly well. Because I don't think I've completely implemented this. One thing you're meant to do, according to the documentation, is you have to rotate the inertial tensor, which I never do, when the thing rotates. So you can also apply your torque around the right vector of the object, and then you can apply force to the object to get it to sort of thrust like that. So that's force being applied in the direction of the look vector. And then there's keys to do roll as well. I can't remember what the keys are. And then off it goes. Bye-bye. Bye-bye, book. Book writers. So that's the full Hamiltonian, and there's this damping applied to it, so it slows down after a little bit. So let's take a short break, and then we'll look at implementing all of these equations in code, all right?